Okay, in this video, we're going to see if the sequence converges or not, and then we'll see if the series converges or not. So let's take a look right here. And it's always a good idea to come with an explicit formula to work with. So we'll see. Notice that we have 1, 1, 1 on the top, and we have 9, 6, 8. 9, 6, 4 on the bottom there. So it's not so clear. But if we look at from 1, 3, 9, we just multiply by 3, right? And then on the bottom, we have 4, 8, 16. That means we just multiply by 2. In another word, we just need to multiply by 3 over 2, right, to get to the next term. And is that so for these numbers right here? And the truth is, it is. When we go from 1 over 9 and multiply by 3 over 2, of course, the 9 and 3 will cancel. You have the 3 on the bottom, and 3 times this 2 on the bottom will give us the 6 on the bottom. And then we can keep going, multiply by 3 over 2, and we can go from here to here, right? So in fact, this is a geometric sequence. And let me just write this down right here for you guys. We can write down AN equals, and let me remind you guys the general formula. We need A1 times the common ratio, and then raised to the n minus 1 power. And this right here is the common ratio, namely 3 over 2. So we can just write down A1 is 1 over 9, and then the R is just 3/2. And we take this raised to the n minus 1 power, and there we have it. This right here is our geometric sequence. Well, to answer this question though, we have to take the limit as n goes to infinity of this, right? So we'll just check. In order for us to see if this converges or not, we take the limit as n goes to infinity of this right here, which is 1 over 9 times 3 over 2 raised to the n minus 1 power, like that. But notice the following. Right here, this is our R, and R in our case is 3 over 2. And this right here is bigger than 1. So that means this right here actually will be infinity. Whenever we have R to the nth power, and then right here you have the minus 1, doesn't really matter. You can fix the negative 1 exponent if you would like. But if this right here is a number bigger than 1, raised to the nth power, and when n goes to infinity, we get infinity. So in fact, right here, AN unfortunately diverges because the limit is infinity, because R is 3/2. Okay? Now let's take a look if we add up everybody from there. So this is a series situation. This right here is asking us to do 1 over 9 plus 1 over 6 plus 1 over 4 plus 3 over 8 plus 9 over 16, and so on, so on, so on. It might not be easy to see, but the truth is that these numbers are getting bigger and bigger because every time we multiply by 3 over 2, which is a number bigger than 1. So the next number is actually going to be bigger than this, and so on, so on, so on. And the deal is that eventually the term is going to be approaching infinity because we did the limit right there. So the truth is, when we add up all of this, let me tell you, this right here will be infinity. So in another word, this right here diverges. So I'll write this down. N goes from 1 to infinity. And perhaps let me just write that down for you guys. I will write down 1 over 9, parentheses, 3 over 2, n minus 1. This right here, it's called the geometric series because we're adding everybody up. Series is when we're adding everybody up. This right here, notice because the R is 3 over 2, which is bigger than 1. So this right here, I will tell you, this series diverges. You can argue it this way because the R is bigger than 1, or you can also say the following. You can also say this, or the series n goes from 1 to infinity of this series. This right here diverges by the test for divergence because we saw that, let me just tell you, because the limit as n goes to infinity of the AN, which is the one that we did over there, this was not equal to 0. So in fact, when we see this was not equal to 0, we can go right here and say it diverges right away. But this is the geometry series form for you, right? So that's pretty much the connection. Okay, we are given this sequence, and we'll first see if the sequence converges or not, and then we'll see if the series converges or not. So here we go. Let's come up with the explicit formula first. And the truth is, if you look at these numbers, okay, we have positive, negative, and so on, right? So it's kind of alternating. So be sure you have -1 to the nth power or something like that, right? And also, we see that the denominator from here to here is just multiplied by 3, and then multiplied by 3, multiplied by 3. So the truth is, everybody is just multiplied by -1/3 because it's positive and you want to get to negative. And then when we go from here to here, again we multiply by -1/3. And check this out. 3 times -1/3, 3 and 3 cancel, you have the negative on the top, and of course the 5 stays the same, just multiply your fractions. And then of course this is the same, therefore this is a geometric sequence. So to get a formula for this, we know an is equal to a1 times r raised to the n-1 power, and a1 is just 3/5. Let's just put that down. And then we multiply by -1/3 for the r, and we take this raised to the n-1 power. So here is our an formula. And now, to see if this converges or not, we have to take the limit. Therefore, we're going to check. We take the limit as n goes to infinity of this guy, which is 3/5 times -1/3 raised to the n-1 power. And here is the deal. Notice that this is like an exponential situation, right? Geometric exponential, same thing, because you have the base being a number, and then we have the n in the power. Whenever this happens, just look at what the r is. The r in our case is -1/3. And when you take the absolute value of r, notice that this right here is less than 1. As long as the absolute value of r is less than 1, let me tell you, this right here will converge to 0. The limit right here, this is equal to 0. So to answer this, we'll say an converges, and we know that it converges to 0, just like this. Alright, unfortunately though, when an goes to 0, we cannot draw any conclusion for this right away. We have to do some more work for that. So now, let's take a look at this right here. First of all, when we have the summation, this means we are going to look at these numbers and then add them up. So for this situation, we will have positive 3/5, and then we add it with -1/5. In another word, that will be just minus 1/5. And then we continue. We add positive 1/15, and then we subtract 1/45 because it's a plus the negative number, and then we add 1/135 and minus, and so on, so on, so on. This is what this means. And of course, if you would like, you can write this down as the summation form. This is the sum as n goes from 1 to infinity, and you put on the an formula, which is this one right here. So I just put that down right here for you guys. Namely 3/5 times -1/3, and then raised to the n-1 power. And because we have talked about this already, this is the geometric series. Well, we just have to pay attention to the r, because we have r equals -1/3, and when we take the absolute value for that, this is less than 1. We know this right here is a convergent geometric series, right? Because the absolute value of r is less than 1. You have to take the absolute value because remember, -2 is also less than 1, but the absolute value of -2 it's not less than 1. And in fact, we know what this converges to. So let me tell you guys. This right here, we'll just write it down. The sum as n goes from 1 to infinity of this 3/5 times -1/3 to the n-1 power, it converges to, well, the formula as I told you, when this converges, all we need is the first term. So we look at the first term, which is 3/5. Just put that down. And we do 1 minus the common ratio, namely -1/3. So just put that down right here, -1/3. And then we just do the little fractions. So this right here is just 3/5 over this is like saying 1 plus 1/3. So this is like 3 over 3 plus 1/3, which is 4 over 3, right? And then you just flip this little thing, and you get this equal to 3 over 5 times 3 over 4. So do your little fractions, and you get positive 9 over 20. So that's it. This right here converges, and in this particular case, we also know that it converges to positive 9. Okay, here we have this sequence, and we'll see if this right here converges or not, and then we'll see if this right here converges or not. And notice this is just a series. In another word, we will add up everybody from there. Anyway, let's come up with the explicit formula for this guy right here. Notice that on the top, we just keep adding 1. On the bottom, we just keep adding 4. Therefore, we have arithmetic on the top and also arithmetic sequence on the bottom. So to do that, in fact, I'll show you guys the quick way to do this first, right? an equals on the top, because the common difference is always 1. So we have 1. Remember, the common difference is a coefficient, and we multiply by n, and then we add it with, okay, when n is equal to 1, put it here. 1 times 1 is 1. We have to add what to get to 7? 6, right? So we just put on plus 6, just like that. All right, that's it. And then on the bottom here, the common difference is 4. So we know that the coefficient right here is 4, and then multiply by n, and we add. When n is 1, 1 times 4 is 4. 4 plus 11 will give us 15. So just add 11 to it. This is the quickest way to do it. And if you would like to use the formula way, let me just write this down right here for you guys. an equals, on the top, I will have to put down 7, which is the first term, and then we add it with n minus 1 times the common difference, which is 1, right? And then on the bottom, to put down the first term, which is 15, and then we add it with n minus 1 times the common difference, which is 4. So you do your algebra, you end up with this anyway, and you can just show me this on the exam. It's much better, in my opinion. All right, this is the an formula. Does this converge though? Well, we have to take the limit, so we have to check the limit as n goes to infinity of this expression, namely n plus 6 over 4n plus 11. And notice that on the top we have a linear situation, likewise for the bottom. We just care about this and care about that because they are the dominating parts when n goes to infinity, right? They are the big boss. And we end up with n over 4n, cancel the n, namely we just get 1 over 4. So the answer for this right here is an does converge, and converges to 1 over 4. And we are done for this part. And now, when we get the limit of an goes to 1 over 4, what can we say about this right here? This 1 over 4 is a happy face because this right here diverges since this right here is not equal to 0. That's it. You don't have to do anything fancy. And here's the idea. Remember, when we are doing this, the summation, this is telling us to add up everybody from the sequence. So it is the question that we have to do 7 over 15 plus 8 over 19 plus 9 over 23 plus 10 over 27 plus 11 over 31 plus ... right? And again, over there, we have done the limit right here already. And the idea is that eventually, we are just adding bunch of the numbers, and these numbers right here, it's approximately 1 over 4. So you can just imagine we're just adding a lot of 1 over 4 after a certain point, and so on, so on, so on. And when you're adding up infinitely of 1 over 4s, this right here will of course go to infinity. In another word, this right here diverges. And let me just show you guys. You are going to encounter the sum as n goes from 1 to infinity of that expression, n plus 6 over 4n plus 11. This is the more typical question you have to deal with. I will tell you this right here diverges, and the reason is because by the test for divergence. And this is all you have to put down because over there we have seen that, right? So this is because the limit as n goes to infinity of this n plus 6 over 4n plus 11. This was equal to 1 over 4 that we did over there. And 1 over 4 is crucial because this right here is not equal to 0. So you can use the test for divergent and to argue that this right here diverges. Okay, we're given this sequence right here, and we'll see if this converges or not, and then we'll see if the series of an converges or not. And as usual, let's find an explicit formula for this first. Notice that we have 1 on the top, so that's nice. So therefore, we know an equals 1 over n on the bottom. Of course, 2, 4, 6, 8, 10, and so on. They are just all the even numbers. So real quick, this is just 2n. That's all. And in our situations here, n start with 1. So you have 2 times 1, 2 times 2, 2 times 3, 2 times 2, and so on. So that's it, right? And of course, to see if this converges or not, we are going to check the limit as n goes to infinity of an, which is just 1 over 2n. And 1 over 2n, if you put infinity here, well, 2 times infinity is still infinity. 1 over infinity, we get 0. Therefore, this right here, an does converge, and it converges to 0. And with that, we are done. But unfortunately though, when an converges to 0, this is technically like a sad face, because we will have to do more work to figure this out if the series converges or not. And remember, whenever of this series, this is asking us to add up everybody. In another word, 1/2 plus 1 over 4 plus 1 over 6 plus 1 over 8 plus 1 over 10, and so on, so on, so on. And we'll see if this converges or not. Well, I will put down a summation form for you guys. This is the sum as n goes from 1 to infinity. An, which is what we found over there, for this is just 1 over 2n. And now, you see that we have 1 over 2. It's just a constant multiple. We can just take that to the front, just like how we did the integrations, right? So, we can look at the 1 over 2, and then just bring that to the front. And we have the sum as n goes from 1 to infinity of 1 over n. Of course, 1 times 1 is 1. So, just like this. And the deal is that this right here diverges. Why? Because this is the harmonic series diverge, right? Harmonic series diverges. So you can just put down something like this. And of course, when you have a divergent right here, 1/2 times the divergent, meaning 1/2 times this right here is an infinity situation. 1/2 times infinity is still infinity. Therefore, this right here, it's still a divergent, of course. So that's pretty much it. And again, because you have the harmonic series right here. So this is enough to show that this right here actually diverges. Okay, in this video, we're going to see if an converges or not. And as we can see, we have sine 2, 2 sine 1, 3 sine 2 over 3, and then 4 sine 1/2, and then 5 sine of 2 over 5. And of course, these are all ingredients. And we will also see if the series of that will converge or not. It's kind of weird. First of all, I do notice that we have 1, 2, 3, 4, 5 right as the coefficient, so that's pretty good. But how about inside? We have 2, 1, 3/2, 1/2, and then 2 over 5. Well, here's the deal. This 2 is the same as saying 2 over 1. This 1 is the same as saying 2 over 2. And then this 2/3, of course, the same as saying 2/3. And this right here is, of course, well, 1/2, we can just look at this as 2 over 4. And now see everybody has 2 on the top. And of course, for the last one, we do have that 2 on the top already. So here is the formula for the sequence an. Check this out. Again, n starts with 1, and we have 1, 2, 3, 4, 5, and so on. So we will have n as the coefficient, and then we have sine function, of course. And then inside here, everybody has a 2 on the top. So let's put down a 2 right here, and divided by n. That's correct. So we have n times sine of 2 over n. So again, 1, 2, 3, 4, 5, and so on. And then we have the 1s, 2, 3, 4, 5 on the bottom. So that's it. However, we still have to take the limit, so let's go ahead and do that. Take the limit as n goes to infinity of an, and this is the same as saying take the limit of this, which is the limit as n goes to infinity of n times sine of 2 over n. Well, for this one, if n is toward infinity, this will be infinity, and 2 over infinity is 0, so sine of 0 is 0, so this is an infinity times 0 situation, but we do have the secret weapon for this one, right? We can use the limit for this. So, to do this, I will first move this n down, so we can get to the form that we want. This right here will be the limit as n goes to infinity, and we have sine of 2 over n over this n down, which is 1 over n, like this. So please do not use L'Hopital's rule, right? Use the limit, just do the code for that. Now, for this one, what we're going to do is just do a substitution. So, let's put a theta inside. So I would say that theta equals to 2 over n, like this. So that's pretty much the idea. And then we will just see that if theta is equal to 2 over n, we get the limit as theta goes to 0. Because when theta is 2 over n goes to infinity, 2 over infinity is 0, so theta is going to 0. And then we'll see on the top is sine of theta. How about 1 over n? Well, let me just write this down right here better. We say theta is equal to 2 over n. Of course, we can divide both sides by 2. So that means 1 over n equals theta over 2, isn't it? Just like that. So we can put down theta over 2 on the bottom like this. Well, this over 2 is on the bottom. We can bring that up. So what we're looking at is this. The limit as theta going to 0. This 2 up here, and then I'll just put down the sine theta over theta like this. And as you can see, this is just going to give you 1 and then times 2. So this right here will be 2 like that. So I will tell you that an converges to 2. So an converges to 2. So that's the idea, because the limit does exist. All right, for second one, hey, because the limit right here, it was equal to 2, huh? So this right here is actually really easy. Why? Because it diverges. Remember, the sum means that we are going to add up everybody, right? And eventually, we are going to add up about, values of 2. And if you're adding up a lot of infinitely many of 2's, you end up with infinity. So the query to say this is that, well, I will just write this down nicely for you guys. This right here diverges by test for divergence. And you have to keep in mind, if this is the question you're doing, always check the limit real quick, because if it's not equal to 0, congratulations, you have the answer already. This is by test of divergence, and let me just write down, because the limit as n goes to infinity of an, it was equal to 2. And you have to mention that 2 is not equal to 0. And that's it. So you have to remember the 0 is the number we're going to use for test for divergence, and later on there will be other numbers will be used for other tests. So that's it. Okay, we are going to see if an converges or not, and then we'll see if the infinite series of an converges or not. So here we go. Everybody has a 1 on the top. That's nice. And everybody seems to have a square root on the bottom. Yes, this right here is the same as divided by square root of 1. And this 2 right here is the same as square root of 4. Therefore, an is actually really nice because it's just 1 over square root of n. Just like that. And our n starts with 1. Then take the limit as n goes to infinity of an, which is the limit as n goes to infinity of 1 over square root of n. You put infinity to here. Square root of infinity is infinity. 1 over infinity, we get 0. Therefore, we know that an does converge. And we'll say an converges to this number, which is 0. And then after that, we are done. Now, for part 2, unfortunately, we have to do a little bit more work because an converges to 0, right? So we cannot use the test for convergence. We cannot use the test for divergence. And when this is 0, we cannot say anything about this unless we investigate more. As a reminder, this right here means what? We are going to add out everybody. So let me just put this down. We are going to add out 1 plus square root of 2 plus 1 over square root of 3 plus 1 over, let me just write it down, square root of 4, and then 1 over square root of 5, and so on, so on, so on. And does this have a finite sum? Well, that's what the question is. And then let me just put on the summation. Look for this. 1 to infinity of an, which is 1 over square root of n. All right, now the investigation begins. It's not that bad at all. Because we have the square root, which is the same as 1/2 power. So we can say this is the sum as n goes from 1 to infinity, 1 over n to the 1/2 power. And here is the p series. This right here, p is 1/2, which is less than or equal to 1. And that means this right here diverges, right? Because again, if you're using the p series, you have to compare the p value here, the power, with 1. This is less than or equal to 1. So this right here diverges by the p series test, or just the p series test. Okay, in this video, we are given the an formula, and we'll see if an converges or not, and then we'll see if the series of an converges or not. So, of course, right here, we are going to take the limit as n goes to infinity, and let's just get that going. This is our check to see if this converges or not. Take the limit as n goes to infinity, and just write this down again, of course. 4 to the n over 4 to the n plus n to the 4th, and then we minus n squared over n squared plus 2 to the n, like this. And now, here is the deal. You can take the limit of the first guy first and then see what happens, and then take the limit of the second guy and see what happens. For the first one, pick the dominating part, and exponential is bigger than and more powerful than power. So, the truth is 4 to the n is much more dominating than n to the 4th. So we just look at this and look at that, okay? And in fact, the limit of the first guy right here is equal to 1. N to the 4th power is going to be so small compared to 4 to the nth power, all right? So we actually have 1 right here. Let me just put that down for you guys. This right here, we get 1. And then let's bring down the minus. And now let's look at the second one. Be really careful. You don't circle n squared and n squared. This answer right here is not equal to 1 because on the bottom here we have 2 to the n, which is bigger than n squared. So on the top, yes, you circle n squared, but on the bottom you have to consider 2 to the nth power. And then by the list, we know that n to the p's power is so much smaller than b to the nth power, right? So this case right here, we actually end up with 0, and all in all, the answer to this right here is equal to 1. That's the answer. And we'll just say that an converges to 1. Alright? So again, 2 to the n, the exponential part, because 2 is bigger than 1, so you consider this. This will be so much bigger than the n squared, so you have to consider this and that, right? And of course, you have to circle the n squared on the top because that's the only thing. So you consider and compare those two things, and that's all. And keep the list in mind, of course. That's it. Now, when an converges to 1, congratulations, we know this right here is what? Yes, diverges. And now I'll just write this down for you guys nicely. I will just put this down, the sum as n goes from 1 to infinity. And you put down the an right here again, which is 4 to the n over 4 to the n plus n to the 4th. And you minus n squared over n squared plus 2 to the n. This right here diverges by the test for divergence. That's it, right? Diverges by test for divergence. And if you want to give a reason, you can say this right here, the limit. And notice that this is the sum, this is just the limit of the an. This part is from the first part. As n goes to infinity of an, which is this guy, that's what we got. The limit was equal to 1. And this, it's good because this is not equal to 0. Therefore, we can draw a conclusion right away. Given this AN formula, if this converges or not, and then we'll see if the series of AN converges or not. So right here, of course, let's go ahead and check our limit as n goes to infinity. And if you look at this right here, we have 1 minus 1 over n raised to the nth power. This right here, of course, we can just use the fact for this limit, right? And the deal is that pay close attention to the a value, which is -1, and the b value is +1, right? Because 1 times n. So I will tell you guys, based on this, I will write down a is -1 and b is equal to 1. And when you're doing this, you are telling me that you are using the fact. And we know that the answer to this is just e to the ab power. And of course, it's -1 times 1. Of course, this is just equal to e to the -1, which is just 1 over e. That's great. In another word, we know that this an does converge because it has a limit. It converges to 1 over e, which is very cool. Very, very cool. Why? Because I don't have to do any more work right here anymore. Because thankfully, an converges to a non-zero number. So this right here diverges right away. Very nice. But again, I would like to write this down for you guys. When we have this question, the question is like the sum as n goes from 1 to infinity, and then you put on an here, which is 1 minus 1 over n raised to the nth power. Now this is the summation. This right here diverges. Why? Again, by test for divergence. So this right here is it. That's the idea. And if you would like, you can also write this down because the limit as n goes to infinity of the an, which is this part. This right here, it was equal to 1 over e from there, right? We got it from there over there. And the best thing is 1 over e is certainly not 0. So, okay, we're going to see if the sequence converges or not, and then we'll see if the corresponding series converges or not. Here we go. We have an is equal to 1 over n squared plus 4n plus 3. So of course, let's go ahead and take the limit. This is not so bad. If the limit as n goes to infinity of an, which is just that, the limit as n goes to infinity of this 1 over n squared plus 4n plus 3. Put infinity here, on the bottom will be infinity. So all in all, we get 0. Therefore, it's a yes. Man, if it's a yes, that means we have to do more work over there. An does converge, and I'll tell you guys that an converges to 0, and then we are done. Not so bad. All right, here, let's see if it converges or not. This is the sum. That means you just add out all the terms, huh? This right here is how it looks like. So we are going to see the sum as n goes from 1 to infinity, 1 over n to the second power plus 4n plus 3. Okay, this right here, in fact, it's a telescoping series. And we'll just work it out. We'll actually tell you guys the value for this as well. Here we go. Let's see. This right here, you can look at this as n plus 1 times n plus 3. We can factor it, of course. And then we can do partial fractions. So this is the same as saying the sum as n goes from 1 to infinity. And then here we have n plus 1 on the bottom. And the other fraction is n plus 3 on the bottom, like this. And of course, we'll do it the cover-up method, doing our head though. To figure out this number, we go back to the original, cover up this, and n has to be what? -1. And you put it here. -1 plus 3 is 2. On the bottom though, so we get 1 over 2 right here. And do the same thing right here. Cover n plus 3, n has to be -3. Put it here, -3 plus 1 is -1 half, right? -1 half altogether. -3 plus 1 is -2 on the bottom. So that's what we have. Now, both of them have the 1/2, so we can factor that out, put that in the front of the summation, just like how we do the integrals as well. So we have the sum as n goes from 1 to infinity, and this is 1 over n plus 1, and that's a minus, and we have the 1 over n plus 3. And a small tip for you guys is that whenever you factor, and this is a telescoping series, always put on a smaller factor in the front. It's easier this way because the minus will be right in the middle. So the subtraction works out very nicely. Okay, what we do is, of course, we should just write down some terms and see the cancellations, all that. But I'll show you guys the fast way to do this first. The fast way to do this is that, okay, ask yourself, n plus 1 and n plus 3, they are off by what? They are off by 2 terms. So that means the following. You have the 1/2 right here in the front. Okay, they are off by 2. That means the first 2 terms will stay, and then like the last 2 terms by the nth partial sum will also stay. Let me explain. First term, you just put 1 into here, so we get 1/2. And we also need another one. We put 2 into here, it's just 1/2. Plus 1, which is 3, like this. So this is what I mean by the first 2 terms. And then we have to subtract. This is how we find the nth partial sum formula, right? Well, the very last term is going to be subtracted, which is this, which is 1/n plus 3, okay? And then a term before that will also remain, which is 1/n plus what? Well, we have n plus 3, that's the nth term when n is equal to n, and just subtract 1, so you just have n plus 2. So that's the idea. So this is the quick way to do it. That's how you get the nth partial sum formula. But remember, you have to take the limit as n goes to infinity. Take the limit as n goes to infinity. Well, the good thing is that this and that will both go to 0. Perhaps I'll put it down with the whole thing because, yeah, the whole thing is going to 0. So let's see if I can add fractions or not. This right here is equal to 1/2 times 1/2 plus 1/3, and let's see. Man, 3 plus 2 is 5/6, so it's 5/12. And just add the fractions for that. All right, so that's the idea. Okay, so now that's okay to do if you would like, but I'll show you guys the write out. First of all, we have the 1/2 all the way in the front. When n is equal to 1, you put it both into the here and here. So we get 1/2 and then minus 1/4. This is when n is equal to 1. And then we add the next term, right, in the next parentheses, which is when n is equal to 2. And when n is equal to 2, you put it here and here, we get 1/3 minus 1/2 right here, which is 5, like this. And then just continue. Plus, next you get when n is 3, so you get 1/4 minus 1/6. And let's just write down a few more. We can still see, let me just put on one more, which is 1/5 minus 1/7. And that's pretty much the idea, right? But remember, you have to consider the nth partial sum. So this is what you do. So in the end, you're going to keep adding. And I'm just going to write down the nth term, meaning that you put n in here and here, which is just, of course, that. So we get 1/n plus 1 minus 1/n plus 3. And this right here keeps on going forever because it's the infinite sum. Okay, if you are off by 2, you should also write down the parentheses in front. And I'll just put this down here for you guys real quick. A term before that, when you have n plus 1, a term before that just 1/n. A term before this is just minus 1/n plus 2. So that's what I mean by that this earlier. All right, now check this out. Look at all this. The red parentheses actually doesn't really matter. And you have the 1/2, okay. Nothing is 1/2 besides that, but doesn't matter. We have negative 1/4. And you see, we jump to here. This is a positive 1/4. This can be cancelled out with that, right? And you see, this guy got cancelled out first. The guy in the first part in the parentheses right here got cancelled it. And check this out. This 1/3 stay, but we have the negative 1/5. This can jump, and then this and that cancel it, isn't it? Well, next you can see, okay, we have negative 1/6, but do we have a positive 1/6 here? Yeah, we just didn't write it down, so this will get cancelled out with this. And likewise, this will be out as well, and so on, so on, so on. And then later on, this cancellation will happen right here as well. And you just jump, and then this is going to cancel it with 1 over n first. And then this guy is going to cancel with this guy. So you stop right here. So that's what I mean by you write down the first two terms and just plugging n is equal to 1 and n is equal to 2 into the first guy right here. So we get a 1/2 and 1/3. That's what we have. And then you minus, you minus the nth part right here, right? Minus this part. The second term right here, right? The second thing right here. And then a term before that. So you have the 2. So it's this and that right here. Minus, and then you do the rest. Okay, we are given an is equal to e to the 1 over n minus e to the 1 over n plus 2. Does this converge? Of course, we'll just take the limit as n goes to infinity. So here we go. We check the limit as n goes to infinity. And of course, e to the 1 over n minus e to the 1 over n plus 2. And of course, we just have to put the infinity into here and here. And it looks like we will have e to the 1 over infinity and then minus e to the 1 over infinity plus 2. Like this. And the deal is that 1 over infinity, of course, that approaches 0. E to the 0 will give us 1. So that's very nice. Similar right here, right? We also have 1 over infinity. So this is also 1. And 1 minus 1, of course, we get 0 for the limit. But this is going to be a sad face for that, right? Anyway, we do know that an converges, and we know it converges to 0. Like that. Now, for the series, this is telling us that we have to add up all the terms from there, right? When n goes from 1 to infinity, an is that, so I'll put on parentheses, e to the 1 over n minus e to the 1 over n plus 2, like this. Well, this didn't work because, again, as n goes to infinity, an converges to 0. This is not going to help us. We cannot use the test for divergence. But the good thing is that this right here, it's a telescoping series. And let me show you guys the quick way to do this right here, right? So let me just skip some line because I will still show you guys the work for the expansion way for this. Okay, you see that this is telescoping because they are of the same kind. E to the 1 over whatever. This is n plus 2. Therefore, they are off by 2. In this case, this is what we do. We first put down 1 in here, and then put down 2 in here, the first two terms. When we are off by 2, you have the first two terms surviving, like right here. So we get e to the 1 over 1, and the other one is plus e to the 1 over 2. Just like that. And then we are going to subtract, okay? So we are going to subtract and subtract. Subtract the nth term from here, namely e to the 1 over n plus 2. And the other one is the n minus 1 term from here, namely e to the 1 over, if you put n minus 1 here, n minus 1 plus 2 is n plus 1. So we have the n plus 1 here. So first two terms surviving like that, and then last two terms you have to subtract like this. And as you can see, this is actually the nth sum, the nth partial sum formula. You have to take the limit as n goes to infinity, like this. This time though, this and that, they don't go to 0. It's only this and that go to 0. So check this out. As n goes to infinity, this goes to 0 and this goes to 0. So all in all, the answer is actually e to the first, which is just e, and then we have e to the 1/2. Let me just write this down. We can also put on the square root of e if you would like. But you have minus 1 minus e to the 0th power is minus 1. And then right here, this is also minus 1 because this is also e to the 0th power. So all in all, finally, I will write down, we have e plus, let me just be fancy and put down square root of e. And then, of course, this is just minus 2 for the answer. It's a very crazy looking answer, huh? So that's pretty much the idea. And if you are okay with this approach, you are done. But if you're not, let me just show you and convince you guys why this is what we need. So check this out. What we need to do first is that putting 1 into the ends here. So we get the first term as e to the 1 over 1, right? And then minus e to the 1 over 3. That's the first term. And then we add. The next term is when we plug in n equals 2. Put 2 here, we get e to the 1/2 minus e to the 1 over 4. And then again, you just keep on going. Next, we put on plus e to the 1 over 3 minus e to the 1 over 5. And then plus e to the 1 over 4 minus e to the 1 over 6. And so on, so on, so on, right? So I'll just put on plus dot 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 and then plus dot dot dot. Well, here is the deal. You're going to put on the nth term right here, which is just this. And you write down plus, and then in parentheses, e to the 1 over n minus e to the 1 over n plus 2. And of course, it keeps on going forever. And you also have to put down the previous term right here. So we just write down n minus 1 here, n minus 1 here. So we have e to the 1 over n minus 1 and minus e to the 1 over n minus 1 plus 2 is n plus 1, like this, all right? And now you'll see that e to the first, right here, and we have negative e to the 1 over 3. This and that can be cancelled here. All right? And the truth is, if you look at it different way, right? If you look at this differently, the first guy, there's nothing in front can be cancelled here. But this guy, you can cancel it with that, right? And likewise, this guy, nothing in front can be cancelled it. And this guy, in fact, you can cancel it with that. So, in fact, from the third parentheses here, this and that can be cancelled it. From the fourth parentheses, this and that can be cancelled it. And then somebody right here can be cancelled out with this, and then somebody right here can be cancelled with that. Again, don't forget this is a jump, right? This you jump, so you cancel that. Now check this out. This guy from this parentheses is going to cancel out with somebody in the front, and this is supposed to be another parentheses. This is a jump, right? And then this right here survive, but this guy can be cancelled out with this guy. You jump this parentheses and you cancel out with some guy right here. Technically, it's the second guy in the parentheses, but that's the idea. So as you can see, you have e to the first, e to the 1/2, and this guy and that guy remained, and then you take the limit. But in this case, don't forget when you take the limit as n goes to infinity, this and that, they do contribute something. Well, you have the -1, so be really careful with that. Okay, does an converge? Of course, we take the limit as n goes to infinity. Let's see what happens. This is our check for the convergence of a sequence. So we take the limit as n goes to infinity, and of course, let's just put this down. Namely, we get 1 over square root of n minus square root of n plus 1, like this. Here is the thing. If we put infinity into here and here, the trouble is that we actually get infinity minus infinity in the denominator. That's no good. That's bad. That's dangerous. In this case, this is what we do. We can actually just multiply the top and bottom by the conjugate of this and see what happens. So when we do that, let me just write this down right here for you guys. We multiply by square root of n plus square root of n plus 1 on the bottom and also on the top, like that. And when we do that, we will see this is the limit as n goes to infinity. And on the bottom, of course, when we have this times that, we just have n, and then minus parentheses n plus 1, right? The square of the first minus the square of the second, so we just have this. On the top, we have this times that, of course, it's just this, namely square root of n plus square root of n plus 1, like this. And now, we see that minus this, of course, they cancel, but in the end, you actually have a -1, right? So, here is the deal. We are taking the limit as n goes to infinity, and we have a -1 on the bottom, -1, And on the top, we have square root of n plus square root of n plus 1, like this. And now the question is, when n goes to infinity, what happens? On the top now, we have infinity instead of the square root, which is still infinity, right? The square root of infinity. And then plus square root of infinity plus 1. Of course, this is easier for us to draw conclusion because this is still infinity plus another infinity, right? Infinity plus infinity, of course, is still infinity. Therefore, on the top is infinity over negative 1. So all in all, this right here is equal to negative infinity. And as you can see, an, when you take the limit, this right here, we don't have a finite value for the limit. Therefore, an does not converge. And we just say an diverges. So that's it. And this is so nice because we can come here. And I'll tell you, if we are doing the sum as n goes from 1 to infinity of an, which is just that, so the look will be 1 over square root of n minus square root of n plus 1. This right here, this series actually diverges by the test for divergent. Why? Because we have seen it over there. Because the limit as n goes to infinity of an, which we saw it was equal to negative infinity over there, and this right here is not equal to 0. So this right here, it's good, right? When you have an diverges, you can just say the series of an diverges as well by test for divergent. So this right here, it's not that bad at all. Okay, here we have this an. Does it converge? We'll see. Of course, this is our check. All we have to do is take the limit as n goes to infinity, and we just put this down, of course. Namely, 1 over square root of n plus square root of n plus 1. This question is actually much easier than the minus version, which is the one that we did before. Well, when we put infinity to here, you see that we have square root of infinity, and we add it with square root of infinity plus 1. This is still infinity, plus this is also still infinity. Infinity plus infinity is still infinity. All in all, we have 1 over infinity. Therefore, the answer to that is 0, which is very nice. And then, of course, we can say that an does converge, and it converges to 0. But as you guys know, this 0 is going to be a sad face for us to do the series question. But it's still good though. We have the answer for this. Right? Now, here's the deal. How do we do this? The sum as n goes from 1 to infinity of an. Let me just write that down right here, of course. So the look is going to be this. The series as n goes from 1 to infinity of that 1 over square root of n plus square root of n plus 1. Well, we don't have too much tools yet. Maybe let's use the conjugate business like the one that we did in the previous video, where we have the 1 over square root of n minus and then the square root of n plus 1, right? That one. So let's try that. So let's break it apart, right, in this fashion. Let's go ahead, multiply the top and bottom by the conjugate square root of n minus square root of n plus 1. Like this and like that. And then hope for the best. Okay, so what do we get? This right here is going to be the sum as n goes from 1 to infinity. Well, on the top, we have square root of n and then minus square root of n plus 1. That's great. And then for the bottom, we just have to do this square, which is just n, and minus, we have to do this square, which is just n plus 1, like this. Which is really nice, right? Whenever we have to multiply out the conjugates. And look at n minus n is 0, and then distribute the negative right here, we get negative 1. And what I want to do next is, because we have the over negative 1, let me put the negative 1 all the way in the front of the summation. So we get negative sum, n goes from 1 to infinity, and here we have the square root of n minus square root of n plus 1, like this. And the reason I don't want to distribute the negative is because I want to keep this right here this way. Look at this. We have the square root of n minus the square root of n plus 1. This is a telescoping series, right? And I want to have the smaller term first, namely the n right here, and then the m plus 1 right here next. So it's n in the square root minus the n plus 1 in the square root like this. So I can do it the short way for you guys. And I'll show you what I mean by that. And I'll convince you guys later. Okay, here we go. I'm going to put on a negative right here. To do it the short way, again, you have to make sure this n part has to be smaller than this n part. This is square root of n and minus square root of n plus 1. They are off by 1. So you put on 1 in here, that will be the first term that you get. So namely square root of 1, alright? And then you're pretty much done. But don't forget, you also have to write this down, and that's the nth term, and you have to subtract this part, which you subtract the square root of n plus 1, like this, right? That's it. And you'll just take the limit as n goes to infinity of this guy. Now just work this out real quick. Well, this is just negative 1. That's not bad at all. So we have negative 1 here. But negative times negative become positive, and we have the square root. And you put the infinity to here, so we have infinity plus 1, like this. Look at this. This is positive infinity minus 1. All in all, we still get positive infinity right here. In another word, unfortunately, this right here diverges because it diverges to infinity. So I just tell you this right here diverges, and you can just say it's a divergent telescoping series. Anyway, let me show you why this is true. Put down the negative right here, and we'll see.
Well, putting 1 here, we get square root of 1 minus square root of 2. This is the first term. And then we add, you put down 2 here, so we get square root of 2 minus square root of 3. And then we add, putting 3's, right? So square root of 3 minus square root of 4, and so on, so on, so on. And then you have to put down the nth term, which is the square root of n minus square root of n plus 1, like this. Right? And then of course this one keeps on going forever.
Now check this out. Square root of 1 survive. In order to do so, again, n goes first, and then the n plus 1 next, right, in terms of the terms wise, and then the square roots, of course. This guy, minus square root of 2, is going to be cancelled out with this. And likewise, this guy is going to be cancelled with that. And everybody else is going to, cancel each other out in between, right? So this is going to cancel with that, blah, blah, blah. And you also see that this guy will cancel with this guy. So that's what I mean. We have to put down this right here, and also put down this right here, and also don't forget the negative. That's it. But if you would like, you can go from here to here on my exams. Up to you. It's a divergent telescoping series. Okay, we'll see if an converges or not, and then we'll see if the sum from 1 to infinity of an converges or not. So let's look at this right here. Notice that we have 2 to the negative 2n times 7 to the nth power, and it seems like we can just play around with the exponent real quick. So what we can do is we can just rewrite this, and we can say this is 7 to the nth power over, bring this down, which is 2 to the 2nth power, and then we can look at the bottom as the follows. This right here, we can look at the 2 being with the 2 first. So namely 2 to the second power and then to the nth power like this. And then you'll see this is 7 over 4, and because both of them have the nth power, we can put the nth power right here. So this is how an actually looks like. And now if we take the limit as n goes to infinity of an, which is the limit as n goes to infinity of 7 over 4 to the nth power, well, notice that this right here is bigger than 1. So if n is approaching infinity, this right here will be infinity. Therefore, it diverges. So I will just tell you guys that no, an actually diverges, right? It didn't converge. So that's the idea. Okay, now does the sum? Well, of course not, because that one diverges already. And let me just write it down for you guys. So this is how the question will look like if you're just doing the sum as n goes from 1 to infinity of that thing, which is 2 to the negative 2n, 7 to the nth power. Suppose you're only doing this, then you can work out the exponents and also get a common ratio, right? And you can say that this right here is the sum as n goes from 1 to infinity. This right here is 7 over 4 to the nth power. you can just say, hey, right here, the R is 7/4, which is greater than 1. So this right here diverges by geometric series test. So GST, I guess, GST, geometric series test. So this right here will be it if you're just doing this from scratch. And usually, this and that goes side by side. You can also say it diverges. This right here diverges by test for divergence because an does not approach 0. One way or the other, I think this right here will be quicker if you're just doing this question on its own, right? So anyway, that's it. Okay, we are going to see if this sequence converges or not, and then we'll see if the series version of that converges or not. So check this out. This is defined recursively, so it's a good idea to just write down first few terms to see if there's anything that we can pick up. So now let's see. First, a1 is equal to 5. That's good. So I will just tell you guys, first one is 5. Then the next term is going to be 2 minus our previous. So we just do 2 minus 5, which will give us -3, right? And then we will do 2 minus our previous term. 2 minus -3 is the same as 2 plus 3, which is 5 again. So again, let me just write this down. This is 2 minus 5. And then this is 2 minus -3. And yeah. And next we get 2 minus 5, we get -3. And then 5, and then so on, so on, so on. So by looking at this, does an converge? No, it does not, because it just keep bouncing between 5 and -3, right? 5 and -3. So let me just tell you guys that an doesn't converge, which means no, an actually diverges. So this right here is it. Well, if you look at this right here, how about the sum if you just add them up? Do not just say, hey, this is, well, actually, however you want to do it, but the proper way to say is that, okay, this right here diverges by test for divergence. You can also just write it down, limit as n goes to infinity of an. This right here, this limit doesn't exist. And doesn't exist, of course, it's not the same as 0. So that's how you can just write it out if you want to just be slightly more specific. So anyway, just quick questions like this. Anyway, that's it. Don't worry, let's just write down a few terms to see what happens. First of all, a1 is 9. a2 is what? Well, remember this is going to be n equal to 2, so you have to use this formula to get a2. First of all, you do 6 minus 2, which is 4. Times the previous term, which is 36, like that, okay? So again, it's 4 times 9, 4 times the previous term, like that. And we do the next one. Let's see, n equals 3. That's going to be 3, and you multiply by the previous term. 3 times 36 is 108. Oh my God, it's getting bigger and bigger. Okay, n equals 4. Put 4 in here. This is going to give you 2 times the previous term. We get 216. N equals 5. Am I really doing this right? 6 minus 5 is 1. 1 times the previous one is 216. Okay. I want to give up. But no, don't give up. Because the next one, n equal to 6. What happens? We will get 6. Yeah, 6 minus 6 is 0. 0 times this guy is 0. What's the next guy? N equal to 7. Well, you get -1 times the previous term, which is 0. So, in this question here, if you want to find out the sum as n goes from 1 to infinity of this, the sum of all this right here, all we have to do is just 9 plus 36 plus 108 plus 216 plus 216, like this. And I want you guys to help me, okay? I want you guys to comment down below the answer because it's been so many hours, so you are going to help me, okay? Seriously, you back me up, okay, for this one. You help me. Right? And of course, on the test, you cannot just put on you help me on the test. You really have to use your calculator to do the work and tell me what the answer is, okay?